Now, welcome to our 13th video, and actually I'm hoping this is our last one for this unit. What we're going to be doing are two calculations of molar mass using colligative properties. So let's take a look at this next example. Eugenol, I like to mix these problems up. Some of them I get from books, but every once in a while, I don't know if I looked this one up or not, but I really liked this one because it's practical. I love cloves. Now, in this case, we want to find what is the molar mass of the active ingredient that gives cloves in part its flavor. So they give us the boiling point of a solution, and they give us some other values. I've got 10 grams of benzene and 0.144 grams of this molecule. Now, this is present in the smallest amount. This is present in the greatest amount. Combine that with the fact that they give us Kb for benzene, and the Kb and Kf's always apply to the solvent. That tells me that my eugenol is my solute. Now, since it says boiling point, remember I said I like to set up the two formulas that we're going to use. So delta Tb is going to be, now they're asking for molar mass, so I'm going to use the fuller form of molality here, mass over molar mass, divided by kilograms of solvent, times Kb times I. And now my boiling point of my solution, I want both of these because that's the information that's provided. And my boiling point of my solvent, I hope you can see my little notations for solution, apostrophe N there, and solvent. Now remember, since it's a boiling point elevation, we add the delta Tb here. Now I like to start plugging my givens in around this framework. We've already identified this as our solute, 144 grams. The molar mass is our unknown. Kilograms, we have to convert that. That's given in grams, and we need kilograms. Some people don't move their decimal places enough. You might want to do this on your calculator if you're concerned about that. We're given Kb, 2.53. Now, what about I? How are we going to find I? Right? Well, it calls it a molecule for one, and it dissolves in benzene. We're going to be working hard throughout the year to study different intermolecular forces and solubilities. Benzene is a non-polar covalent molecule. It's not going to dissolve ions. And so we're going to note that I is equal to 1. Normally, I think you would be given a little bit more information. Personally, when I see the word molecule, I tend to think covalent. It's not used ubiquitously that way, but I'd like to keep those separately, that if it's molecule, it's covalent. Compound, it's ionic. Now, they give us the boiling point of benzene. You don't memorize those things. Those will be given, or it would be your final ask. And it also gives us our boiling point of our solution. Now, depending on the problem, I mean, there will be some later on that you'll see where boiling point of the solution is your ultimate unknown. But we know which way to start. We've got two possible formulas. We're going to start with this one because right now, the top one has two unknowns, right? The top one has the boiling point change as an unknown, and it also has our ultimate molar mass as an unknown. So we're going to solve the first one, the second one actually, but this number one here, get delta Tb. So delta Tb, if you do that quick algebra, is 0.22. So I'm going to take that value and I'm going to plug it in right up here. So this becomes 0.22. I hope you see how easy it is when you lay it out on the grid. Really gives you direction. If you're stuck on a problem, start writing down formulas and things you do know. I am not going to go through the steps of this algebra. I'm going to assume you can do that. And if you did, you'd find that the molar mass of this molecule is, I guess we better go to 3 sig figs. I'm going to stick with 3 sig figs to be safe here. 166 grams per mole. Now, if you get a molar mass less than 1, you probably have the inverse of the molar mass, because molar masses can't be less than 1, right? Hydrogen's 1, so everything has to be 1 and greater. So sometimes if you do your algebra and you come up with a decimal point fraction, it's probably because you solved 1 over the molar mass instead. Now, again, I'm going to recommend that you pause this and try you do it 18, excuse me. And if you do, the answer for 18 should come out to 127 grams per mole. And give that a shot, pause the video, try it on your own, and you'll have a better idea of what questions to ask me at the beginning of class next time. I'm going to forge ahead and go ahead and squeak that one into this video. This time we're talking about a molecule called azulene. You notice that it only has carbons and hydrogens. We call those hydrocarbons. And we discussed this earlier. That is a covalent substance, an organic, specifically covalent, and I is equal to 1 for those. And notice that this gives us an empirical formula. Wow, that tricky, naughty AP loves to integrate almost everything we do. This isn't quite AP, but this is exactly up their alley. So we have our solute, we have our solvent. It's benzene, but this time it's the freezing point. So we have a different K value, and we have different values for the freezing points of solution and solvent. So we're going to throw down our two formulas, the change in freezing point. Since we're looking for a molar mass, I'm not a molality, I'm going to go ahead and write out the fuller form over kilograms of solvent times Kf times I, which we now know is 1, but I'm going to go ahead and write it just to be complete. And freezing point of our solution is equal to the freezing point of our solvent. Now remember, it's boiling point elevation, freezing point depression. So we have a subtraction there for our delta TF. Other than that, this is solved very similarly. And if we go ahead and plug in our values here, 640, don't forget to change this to kilograms from grams. Kf is that 4.9, I was 1. TF of the solution was the 5.25, and of the pure solvent was 5.5. So we are first going to solve for this. If we plug that in, we get 0.25. And then if we solve for our molar mass of our molecule, we're going to get 126.7. Now, what's interesting here is it didn't just ask us for our molar mass, and that's grams per mole, by the way. It asked us for our molecular formula. Wow, we have to really dredge back in our memories and find that our number of empirical formula units is equal to our molar mass of our molecule over the molar mass of our empirical formula. And we'd have 126.7 over, now we would have 5 carbons. I hadn't calculated this one, so I'm going to have to do this real quick. 5 carbons plus 4 hydrogens should give us about 64.09 or so. And you can probably tell from looking at that that should give us 2. Remember, this has to be a whole number. So that means there are 2 of these empirical formula units. We just have to do pre-teaching in AP very often because of the integrated nature. 2 times 5 is 10, 2 times 4 is 8, so our molecule should be C10H8. If I did my fast little math there, I didn't have it on my little cheat sheet for you. You could also do a percent error. You could also calculate the molar mass of this, and our percent error, if it had asked, I'm just adding bonus information. I won't even charge you for it just because I love you so much. If you calculated the true, it'd be 128.17 minus the experimental, 126.7. And I don't like to do absolute value. Many people will. I like to know whether I'm too high or too low. You wouldn't be marked wrong on AP if you did absolute value. Times 100. And we get a 1.14% error in this experiment. Actually, pretty darn good. All right, that's your first taste of flipped. We are done with tools of the trade, and we're going to be focusing in class on your WebAssign and practicing those AP questions.